Hello everyone, welcome to my presentation. Today I'm going to introduce our paper, Need for Mobile Speed, a historical analysis of mobile web performance. This is a joint effort with my colleagues at Stony Brook University. There are more than 4 billion internet users, and World Wide Web is the main portal to access information. Based on a report, a 1 second delay in page load can cause 7% loss in conversion rate. The conversion rate is the percentage of users who visit the site and take a desired action, such as buying something on the site, and can lead to 11% fewer page views and 16% decrease in customer satisfaction. So web page loads are extremely critical today. Mobile web performance is even more critical, as 52% of devices used to browse websites are now. Since mobile browsers are so critical, there have been a lot of efforts to improve them, and as a result, mobile browsers are continuously evolving. There exist hundreds of mobile browsers on Android Play Store only, and with every new version, vendors promise a better performance. Anecdotally as well, there is a general agreement that mobile web performance has improved over the years, and in fact, we observe that for 3 sample browsers we have tested, Chrome, UC Browser, and Opera, web user experience has been improving over the years. Our goal is to study the evolution of mobile browser user experience from 2015 to 2018. We want to study how the user would have experienced the page load process in 2015, 16, 17, and 18. In other words, we want to emulate the 2015 user experience when a user is browsing on web pages from 2015 on a 2015 phone and operating system using network conditions that were prevalent in 2015 and compare it to the user experience in 16, 17, and 18. The reason we want to study the historical performance of mobile browsers is because we want to understand the factors that have contributed to the improvement in mobile browser performance. There are several factors that can result in the improving browser performance over the years. Is it because of better browsers, improved network conditions, newer hardware, or optimized web pages? It is important to find what factors play a more important role, as these improvements are not universal. Only 7% of mobile connections across sub-Saharan Africa in 2018 were 4G. If network is a dominant factor in performance, then people in sub-Saharan Africa are unlikely to see improved web performance. Also, phone budgets are different across different regions. For example, Intex MX4, which costs around $60, and Gioni, which costs around $150, are 2 popular phones in India, while in US, more expensive Samsung and Apple phones have the lead. So, if the phone's hardware is the key reason for the performance improvement, then this improvement will most certainly not be used. To understand the important factors involved, we conduct a historical study using 8 popular mobile browsers: Chrome, Opera, UC Browser, Yandex, Baidu, Web Explorer, Firefox, and KS Mobile across 4 mobile devices. And we choose 150 websites out of 2,000 pages from Alexa's top 1 million sites to cover different page sizes. We randomly choose 50 pages for each bucket: light, less than 1 megabyte, medium, 1 to 3 megabytes, and heavy, greater than 3 megabytes. These pages were retrieved using Internet Archive's Wayback Machines API to reflect the period of time these pages were being used from 2015 to 2018. And in total, we ran over 250,000 experiments. To study historical performance, we emulate performance of web browsing as experienced by an average user from 2015 to 2000. To quantify payload performance, we use 3 most popular metrics. Payload time, or PLT, is the time between when the page is requested and when the onload event is fired by the browser. PLT is the most common metric used to measure payload performance. Recently, 2 other metrics have been introduced to better quantify page performance from the user's point of view. The speed index is a visual metric that measures the average time for visible content to appear on the browser viewport. The speed index is measured over a video of the page load process. Time to interactive, or TTI, measures how long it takes for a page to become interactive. Example interaction include clicking on a link or using the autocomplete feature of a search bar. We show results based on PLT in this tag, since the other metrics follow the same trend in our However, there are challenges in measuring web performance. First, content variation. When we browse a website, there is no guarantee that the content remains the same when we browse the same URL later. This has a major impact on what we are measuring. The same argument is true for the access network. An interference in the wireless signal can lead to an increase in delay, which consequently would increase the page load time. And last but not the least, most browsers provide a management interface so that an automation script can programmatically control the browser's behavior. However, these interfaces are not universal. For example, Chrome has its own remote debugging protocol, and Selenium supports only a few browsers. We need a more generic approach. In order to address these issues, we have designed a controlled environment to mitigate content and network variations. Also, we take a more general approach in performance measurement that is supported by almost all browsers. As the very first step, we record the content of selected web pages for each year using Internet Archive's API and store them locally. We then spin up a replay server. The replay server loads the recorded archive file and acts as a web proxy to serve all incoming HTTP requests from mobile devices under test. This way, we ensure that similar contents are being served during an experiment. Then, experiment automators apply desired network profiles to emulate network conditions for each year and also to limit the probable fluctuations. And the experiment automator is continuously managing the experiment by installing new instances of mobile browsers on devices, by passing splash screens, and loading pages while launching the relevant activities through ADB. For each page request, a script is injected into that web page in order to collect performance metrics. This script is based on JavaScript performance interface that is widely available across different browsers and is not bound to only a limited number of browsers. In parallel, a video of each page load is also being recorded and then pulled onto local storage for further analysis. We use this video to calculate the speed index metric. The injected script sends the remaining metrics to our web server via an AJAX call. This transmission happens after onload event is fired on the page. These metrics data are received on our web server by a PHP program and stored locally as JSON files. Overall, our testbed provides a controlled environment to mitigate content and network variations. We use Google's WPR web page replay from Catapult project as our record and replay server to serve similar contents for all of our experiments. We also use Linux traffic control TC utility to control network parameters. The testbed also provides a general framework capable of managing a variety of browsers. We have customized Hindsight, which is a browser-agnostic security framework as our experiment automator to install different mobile browsers on their different Android versions. Hindsight takes care of fresh installation to guarantee a cold start, bypasses any splash screen, and launches appropriate browser activity through ADB. And finally, the testbed is a metric collector. We inject Akamai's Boomerang script in each page we serve. Boomerang is a JavaScript library that measures the performance characteristics of real-world page load and interactions. To emulate network conditions for each year, we applied network profiles according to Cisco's Visual Networking Index to reflect an average user in the world. For example, 2015 environment indicates an environment in which the network is the average network available in year 2015. Browser versions are those released in 2015, running on top of an Android device that was widely used in 2015, along with web pages from mid-2015 as captured by the Internet Archive. And similarly for 2016, 17, and so web page performance are improving. But let's get back to our original question. Which factors are causing this improvement? Is it because of optimized web pages? No. We find that web pages are becoming more complex. This is also aligned with previous studies, and we are not going into details for this. Is it because of better access networks? We find that network impact has saturated. Is it because of better browsers? We find that browsers are becoming more bloated and less performant. We find that this increased performance is due to more powerful underlying hardware and operating systems. In fact, the improved hardware masks the slowdown of newer browsers versions and complex web pages. This has a significant implication for many regions across the globe that do not have access to newer phones. Let's get into details. We find that 2015 browsers outperform 2018 browsers when running on the 2018 mobile device. This is the page load time distribution for Chrome browser running on 2018 device, and this is a 2015 device running 2015 Chrome browser. We observe that older Chrome and older device perform better than newer environments when all other factors are kept constant. Similarly, the 2018 browser is slower than the 2015 browser when both are running on top of a 2015 mobile device. Since all other factors were kept constant, this demonstrates that newer versions of browsers are slower than their older counterpart. Newer browsers are bloated usually to add more features, but it comes at the expense of the performance. And similar trend is observed for Firefox and the remaining 6 browsers. Others in this plot is representative of the median value for the 6 remaining browsers we have used in our method. In another finding, we find network impact has saturated. This graph shows the network impact result for Chrome browser. Here we applied different network conditions to a recent browser and device. We again keep all other factors constant and load 2018 web pages on 2018 device and browsers. This is 2018 network on 2018 device, followed by 2017, 16, and 15 networks. The performance jumps between 2015 and 2016 network is the highest here, with further improvement in network condition from 2016 to 2018. There is only modest improvement in PLT. Similar trend is also observed for Firefox and remaining 6 browsers in this plot. As you can see again, the performance jump between 2015 and 2016 network is the highest. We find that the increased performance is due to the more powerful underlying hardware and operating system. This plot depicts the computation time for the same experiment for different pages across different devices. Computation time here is total time of compute activities on the critical path. Critical path is the longest path on the page dependency graph composed of compute and network activities. We employ WPROF X to calculate the computation time. Here, we use the term contemporary to refer to using the version of pages that correspond to the underlying environment. For example, 2016 pages were contemporary to the 2016 browsing environment. There, we again observe that the mobile devices spend less and less time on computation, even though pages are becoming increasingly complex. And on a side note, we also find that browsers are not similar. We observed little difference in median web page load performance across 8 browsers that we tested. However, when we plotted the difference in median PLT between the best performing and worst performing browsers for each website, we find that even though for 13% of the web pages, all browsers have similar median performance, for remaining 87% of the web pages, the difference in browser performance ranges from 2 seconds to 12.9 seconds. However, we could not find any correlation between these performance differences across browsers and web page features. To conclude this talk, we find that the underlying hardware of newer mobile devices is the key driver of mobile web improvement. Older browsers run faster than their newer counterpart on the same hardware, and network improvement provides diminishing returns in terms of page performance. We have shared the code at my GitHub. You can see the address here. Thank you. And now I take questions.